Okay, ladies and gents, what we're going to do is a quick video, our last video, thankfully, probably for you, of the statistics unit. We're going to take a look at histograms and something new for us, at least in the class, referred to as the empirical rule. So let's go ahead and take a look at them. So first of all, we need to discuss different types of data or measurement distributions. And one of them gets the all too exciting name, the one that we're concerned with, called the normal distribution. And we're going to talk in just a moment, what does it mean to be normal? But let's just take a look at what it looks like. A normal distribution looks like a histogram like this. And we're also going to start seeing, maybe we won't see the bars all the time, but maybe we'll see sort of this line graph that gives us this smooth bell shape over this normal distribution. So this is what's referred to as a normal distribution, and that's what we're going to study today. The analysis in this video will not apply to something like this that's not normal. And you can see there's some similarities, but we don't have that symmetry. It's not shaped like the bell in this case. So again, this is what we're going to focus on in today's lecture. So our candies, for the most part, were normal. And let's just talk a little bit about what that would actually mean. Here's the normal distribution in the middle here. So what does normal mean? Well, it means that if you have this nice bell-shaped, the mean, the median, and the mode are all going to be really close to each other. And that's going to give us a distribution of measurements or a distribution of data that looks like this. And these other ones, we'd call this one left skewed, where the mean is a little bit to the left of the high point, and this one would be right skewed. Again, we're not going to study those. But what does it mean to have this distribution? Well, it means half of the measurements are less than the mean. So if this is the mean measurement right here, half of them are over here. They were maybe shorter or less massive than the mean. And then the other half is greater than the mean. So this shows us things that are greater than the mean. So if we go to our candy, what we did, our candy was more or less normally distributed. And again, it's don't see the perfect thing, but what we're looking for are general shapes. What we have in here. So in this case, this was for Mike and Ike's. And you can imagine connecting this with something that more or less looks like that smooth bell-shaped curve that would go like that. We also have an indication that it's probably modeled well by this normal distribution by looking at the mean. So the average mass of Mike and Ike's was 1.56. So that would occur right around here, near one of the taller points of the graph. The median of the Mikes, half were greater, half were less. That was 1.6, so that's really close to the median. And the mode was also 1.6. That's what occurred most often. So everything is pointing, the shape of the graph and these values are pointing to the fact that this is probably well described by a normal distribution. So what do we do? Why does that matter? Well, when we have something that's normally distributed, we can make a lot of statements and a lot of comparisons relatively easily. And that brings us to this idea of the empirical rule. So the empirical rule, it's also called the 68, 95, 99.7% rule. So we'll see why we just call it the empirical rule. Basically takes our normal distribution and it chunks it up in terms of standard deviations. So that's all we're looking at here. Remember, the Greek letter mu is our variable for mean or average, and then the Greek letter sigma is our variable for standard deviation. So that's all we're looking at here is a normal distribution. If it's normal, average should be near the peak, and then as we go away, we're so many standard deviations away from the mean. So from the center, we add or subtract multiples of standard deviation. That's what all this is saying. This right here, this would be a measurement that's the average plus 1 standard deviation. This would be the measurement that's the average plus 2 standard deviations. Measurement average plus 3 standard deviations. Opposite on the other side, these would be lower than the mean. So this is the mean minus 1 standard deviation, the mean minus 2 standard deviations, and so on, the mean minus 3 standard deviations. That's important because if we have something that's normally distributed, we can make some statements about what's going to occur or what we predict to occur in a population of measurements. So here's just that thing expanded, right? Let's just take a look at it. So here's the mean. And what does it mean to be within 1 standard deviation? It means that 68% of the data if something is normally distributed, 68% of the measurements will be within one standard deviation. They might be a little bit to this side greater than the mean, or they might be a little bit less than the mean, but most of your data, 68%, is going to occur in here. A little rarer then would be past one standard deviation. So a measurement plus more than one standard deviation would be here. A measurement minus more than one standard deviation would be here. And that's going to count almost all of your data. 95% of your measurements in something that's normally distributed will be within 2% of your standard deviations. So almost everything that you measure should be within 2 standard deviations. But of course, we always know that there's exceptions. So if we go all the way out to 3 standard deviations above the mean and 3 standard deviations below the mean, that's going to cover almost everything you could imagine. 99.7% of all measurements, again, if it's normally distributed, will be within 3 standard deviations of the mean. So how are we going to use that is what we're going to take a look at next. So what we're going to do together as a class is there's lots of things where normal distributions occur. Candy was one of them. Our project that we're going to be working on soon is probably going to give us a normal distribution. Another one is going to be an IQ test. So if we take a look at the IQ tests, the way IQ tests work is they give the test to lots and lots of people. And on average, right, this is the distribution that we see. And what they do is they score or they standardize that test, and they make the average, the score that most people get. They say that that's 100, right? And then if we score better than 100, we're over here, and if we score less than 100, we're over here. So we see as we go this way, fewer and fewer of us, as this curve comes down, are scoring greater than 115. Fewer and fewer of us are scoring greater than 130. Very few score greater than 145. And the same is true on the other side. Fewer of us are at an 85 level for IQ, even fewer at 70, and very few of us would be below 55 in that case. So what we're going to take a look at then is an IQ test distribution, and one of the things we need to know is that the standard deviation is 15 points for this. And so that's kind of nice. The average value, the average score on an IQ is 100, and then the range bins on here, or the bucket widths as Google calls them, this is 1 standard deviation. This is 2 standard deviations. Just adding 15, that's 3 standard deviations. This is 1 standard deviation below the mean. 2 standard deviations, 3 standard deviations. So I'm going to ask you some questions on how to interpret this as we practice and organize our thoughts about this.